This is the third of 4 videos for this course. Superposition states for particle in a box in one dimension. As important and interesting as energy eigenfunctions are, these are just the beginning. We will explore superposition states for particle in a box in one dimension, both generally and specifically, and then watch simulations of their time dependence. For a given system or problem or Hamiltonian, a superposition state is some or any static linear combination of two or more independent eigenfunctions. Of some given operator, we will use energy eigenfunctions. We have the time-dependent superposition state wave function, which is capital psi of x and t is sum over integer n of some constant c sub n, which could be real or complex, times energy eigenfunction capital psi sub n of x and t. An example is 2 over square root of 5 psi sub 1 plus 1 over square root of 5 psi sub 2 for a particle in a box in one dimension. Superposition states, they can exist, they do exist, and they are important in physics and also to modern quantum mechanical technologies like quantum computing. We will consider superposition wave functions that are themselves normalized. So the energy eigenfunctions will be normalized and the superposition wave function will be normalized. And the requirement that will make that be the case is that the sum over all n for the superposition wave function of c sub n conjugate times c sub n be 1. And that's the same as saying the sum of the magnitude squared of the constants is 1. You'll notice that I did that in this example. The magnitude squared of this constant is 4/5. The magnitude squared of this constant is 1/5, and they sum to 1. We want to learn how superposition states are different than energy eigenstates, but we want to do as little math complexity as we can get away with. For the rest of this video, we're going to use the following simple normalized superposition state wave function, combining the ground state, psi sub 1, and first excited state, psi sub 2, for a particle in a box in one dimension. This psi sub s, s for superposition, is this linear combination. We're going to, in our case, restrict ourselves to alpha and beta being real, but we're going to allow a complex phase on the second term, and e to the I theta, and we're going to, so theta will be real, alpha and beta will be real, and we're going to take alpha and beta to be greater than 0. We're also going to require that alpha squared plus beta squared equal 1 so that the superposition wave function is normalized. So for particle in a box, psi sub s, that we're going to look at as an example of superpositions, it's alpha times the time-dependent energy eigenfunction for the ground state, plus beta e to the I theta times the energy eigenfunction for the first excited state. Now here, E1 is not equal to E2, E2 is a higher energy than E1. And so this superposition wave function, it is not itself an energy eigenfunction. It cannot be factored or separated as a spatial portion times a complex exponential time dependence. And therefore, its probability density is going to be time dependent. This is the probability density. You just take the wave function conjugated times the wave function. And we're going to do that for this wave function, psi sub s. If you do the math, you will get the following. The probability density is 2 over L, a normalization factor, times the entire expression in square brackets. Alpha squared sine squared k sub 1 x, that's time independent, plus beta squared sine squared k sub 2x, that's also time independent. But then we have this third term, 2 alpha beta sine k1x sine k2x cosine omega t minus theta. That's time dependent. Now, this is the probability density for x in the box 0 to L, and it's 0 elsewhere. Now, this omega, if you do the math, this omega comes out to be energy 2 minus energy 1 divided by h bar. This probability density for the superposition state, the probability density is real. There's no longer any complex numbers in this equation. So it's real just as the energy eigenfunctions probability densities were real. However, this probability density for the superposition state is time dependent, unlike the energy eigenfunctions probability densities. This probability density for the superposition state is periodic, cosine omega t minus theta. It's periodic with period capital T 2 pi over omega equals 2 pi h bar over E2 minus E1. Now, if you were to integrate that probability density from 0 to L, you would get 1 because I have properly normalized the energy eigenfunctions and properly normalized the superposition wave function. So if you integrate the probability density, you will get 1, and it'll be time independent. Now, let's take a concrete example from that. So psi sub u is a single example of psi sub s, where I've taken alpha to be 2 over square root of 5, beta to be 1 over square root of 5, and I'm using theta to be 0, so e to the I theta is 1. So we can plug these into the formula for the probability density, and here's what we get. It is time dependent, of course. Now, let's graph this. The way that I'm going to graph it as a function of time is I'm going to pick 5 particular times. So I'm going to graph the spatial function at 5 different times. I'm going to separate them vertically, and I will explain. So I'm going to take the particular values of time that correspond to the quarter wavelengths, the quarter periods of the time dependence of the cosine omega t term here. So omega t being 0, pi over 2, pi, 3 pi over 2, and 2 pi. For a particular omega, this would turn out to be 5 particular times. Now I'm recycling this diagram, so the diagram doesn't, this says A instead of L, but anytime you see a little lowercase a in my diagrams or my formulas, it's the same as capital L. I'm just recycling some material. So probability density, the horizontal axis is position. Left of 0 is beyond the left wall. Probability density is 0. Here we have inside the box 0 to A, 0 to L, and then to the right of A or L we are outside the box beyond the right hard wall, and the probability density is 0. So this lower green curve is an example for omega t being 0, and the green curve is the probability density, and the green dot is the expectation value of position at time t equals 0. So in this case, there's non-zero probability for being anywhere in the box at time t equals 0. But the expected value is here, that dot, which is not exactly the peak of the probability distribution. There's no reason why it had to be. In fact, you can kind of see that the probability density is more scrunched on the left and less scrunched on the right, and so the expectation value is a little to the right of the peak. So the green curve here is for omega t equals 0. This second curve up, this red curve, is for omega t equal pi over 2. And here, the probability distribution is more spread out. It's equally spread out between the left and right halves of the box. This vertical black line is the center of the box. So at this time, the probability density is symmetric around the center, and the expected value of position is the center of the box. The next curve up, this blue curve, is omega t equals this was for 0, this was for pi over 2, so this is for pi. And notice that this is the flip of the green curve, flipped around the center. And then when we advance time another pi over 2, we get a curve which is identical to this red curve, and then we advance time another pi over 2, and we get back to the original curve. So the probability, if we were to look at the probability curve is sloshing left to right, right to left, then back and forth. So it's here, and then it sloshes more toward the right, and then it sloshes more toward the right, and then it sloshes more toward the left, and then it is more toward the left, and the expectation value goes here to here to here to here to here. So this is a little bit like the classical particle, which was bouncing off the left wall, then the right wall, the left wall, then the right wall, except here it's not a classical particle, it's a quantum mechanical particle, and in this case, this time dependence is because of a superposition of two energy eigenfunctions. So the superposition state is sloshing its probability left to right, right to left, but the expectation value never bounces off the wall. The expectation value stays within the box. So the probability density is changing in time. The dots are the expectation values for position at those times. In this case, there are no nodes in the probability distribution, no points within the box where there is 0 probability density for the particle being located at that point. But that's just an accident of the particular superposition I took. Typically, superposition states could have nodes within the box at different times. Superposition state expectation values. Now, we have an earlier formula for calculating expectation values for certain observable operators. Our earlier formulas were for a general wave function. We can apply that to the superposition wave function, psi sub s. We have an operator, x, for how to find the observable, the position of the particle. I'm going to skip the math steps in this lecture, but if you want to see the math, that is available in a different, longer lecture here. So if you want to see the math for this case. So here's the expectation value of energy, in which case the observable operator is the Hamiltonian operator. So the expectation value of energy for the normalized superposition wave function psi sub s. So the expectation value for energy is alpha squared. Remember, alpha here is real, so I didn't have to write magnitude squared. Alpha squared E sub 1, the energy eigenvalue for the ground state, plus beta squared E sub 2, the energy eigenvalue for the first excited state. And beta squared is 1 minus alpha squared. That's a condition in order to keep the wave function normalized. So the expectation value of energy for this for a superposition state of multiple energy eigenstates, it's a probability weighted average of those energy eigenvalues, and it's independent of time. Alpha squared is a constant, beta squared is a constant. The expectation value of energy is real, as it will always be for an observable. Alpha squared is real, E1 is real, beta squared is real, E2 is real, so the expectation value for energy is real. In this case, the expectation value for energy is going to be between E sub 1 and E sub 2. Maybe you can envision that. It will not be E sub 1 as long as beta is not 0. It will not be E sub 2 as long as alpha is not 0. The expectation value of energy is independent of time, even though the probability density is changing in time, and so would the probability current, which we haven't described in this lecture. So the probability density is moving in space and time, but the energy, the expectation value of energy, is independent of time. The expectation value of energy is independent of phase theta. Now, so the expectation value is not E sub 1 and it is not E sub 2, it's in between E sub 1 and E sub 2. Well, what does this mean? What if we make a measurement of energy? Are we going to get the expectation value, or what are we going to get? This is an unusual aspect of quantum mechanics. If we make an energy measurement on the superposition state, psi sub s, we will either get energy eigenvalue E sub 1, or we will get energy eigenvalue E sub 2. We will not get the expectation value, which is in between them. The probability of getting E sub 1 as the measurement outcome is alpha squared. The probability of getting E sub 2 is beta squared, which is equal to 1 minus alpha squared. Now if we go back and look at this expectation value, we can reinterpret it as the expectation value of energy is E sub 1 times the probability that we will measure, that our measurement will produce E sub 1, plus E sub 2 times the probability that our measurement will produce E sub 2. So it's the sum of probabilities times energies. This system is not classical. The expectation value of energy is not generally the arithmetic average of E sub 1 and E sub 2. It's weighted by the probabilities alpha squared and beta squared. It would be the arithmetic average only if alpha and beta were equal, being 1 over square root of 2. Now, what happens after we make a measurement? After making an energy measurement, the system has changed irreversibly. It is said to have collapsed to either energy eigenstate psi sub 1, if the measured energy was E sub 1, or it has collapsed to energy eigenstate psi sub 2, if the measured energy was E sub 2. After measuring the energy, the system is no longer in superposition state psi sub s. The expectation value will not generally equal any of the energy eigenvalues, so will generally not be the result of a single energy measurement, which is always one of the energy eigenvalues. There is uncertainty in the energy. We have a formula for calculating uncertainty. The uncertainty in energy, delta E, is non-zero for the superposition state. The superposition state is therefore not an energy eigenstate. We could calculate delta E, it's just using the formula, but we're going to skip that math. So, what does this expectation value of energy mean? If we wanted to take multiple energy measurements and use them to calculate the expected value of energy, maybe if we have a problem where we don't know all the information, and so we would like to experimentally determine the expected value of energy. Well, we cannot do that on a single system, a single atom. The expectation value is a probabilistic quantity. If we wanted to measure it, we must have a large ensemble of systems prepared in the same identical state and take one energy measurement per system. Or we could keep reusing the same system if we had an absolute way of resetting the system back to the original superposition state. Although generally we're not really usually able to do that. So we can understand the expectation value of energy as a probabilistic thing. It's more complicated to actually put multiple systems into the same identical state and then do an experimental measurement of expectation value of energy. This is different than classical mechanics. In classical mechanics, we always assume that we can measure position and momentum and energy always without changing the system. So this is different. Now we can find the expectation value of position. Position is an observable operator. We can plug it into the equation for the formula for expectation value. And if we would do the math, we would get that the expectation value of x, the expected position, is this result: L over 2 minus 32L over 9 pi squared alpha beta cosine omega t minus theta. Now notice, this is a cosine of omega t plus an L over 2 term. So it's a sinusoidal wave oscillating around the center of the box. The expected value of position for this superposition state varies in time, oscillating around the middle of the box. If we take the expected value of position and we average it over one period of oscillation, the average expected value is L over 2, the middle of the box, because we're oscillating around the middle of the box. The amplitude of the oscillation is this term, and at most it can be this value, less than a fifth of the length of the box. So the expected value of position always remains within the box. We can plug in our definite values for alpha and beta, and we find this oscillation amplitude. Let's graph that as a function of time. So here's the box 0 to L, which is A in this graph. Here the vertical axis is time, and here what we're graphing is expectation value of x, which is a function of time. In fact, it's a periodic cosine wave oscillating around the center of the box. Now momentum is also an observable, and we have a formula for the momentum operator, and we can plug it into the expectation value formula, and we can crank the math, which in this case would require a little calculus, and we get the following. The expectation value of momentum operator P is these constants times sine omega t minus theta. The expectation value of momentum for this particular superposition state, it varies in time, oscillating around zero momentum. Recall that for an energy eigenfunction, the expectation value of momentum is 0. And here for the superposition state, the expectation value of momentum is oscillating around 0. Now, if we average this over one period of oscillation, the average over time is 0, and we would expect that. Now, the maximum amplitude this can be for any alpha and beta that are constrained to normalize the wave function, there is a maximum amplitude for the oscillation. And for our particular alpha and beta, if we plug these in, we get a definite value, a definite equation for expectation value of momentum, and a definite value formula for expectation of value of position. Let's graph these one against the other using time as a parameter. This might not be familiar to you, so don't worry about it. So horizontally we have the box 0 to L, 0 to A. Vertically, I'm showing expectation value of momentum as a function, which will be a function of time. Zero here is zero momentum, this horizontal black line. This vertical black line is the middle of the box. The green curve is plotting the expectation value of position against the expectation value of momentum at different times, actually at all times. So I'm pointing here to the bottom of this ellipse. That is a particular time. Time advances in this curve in a clockwise fashion. So the expectation value of position and momentum here, a short time later, moves to here, to here, to here. And at some time here, the expectation value of position is as far left as it's going to get. And the momentum is zero. And the momentum is now switching from negative to positive, and the expectation value of the particle moves here and here and here. Now, this is showing us the time motion of the expectation value of position and momentum for the particle. And if you're familiar with classical mechanics and a classical oscillator, you know, there's a similar kind of graph of the actual definite position and definite momentum of an oscillator. But here, this is a quantum mechanical system. We're graphing the time-dependent expectation values of position and momentum, not the instantaneous position and momentum, which are undefined for a quantum mechanical system. So beware. Do not think of this as a trajectory of a particle. The quantum mechanical bound state does not have a trajectory or a classical motion. It has a probability density, probability current, expectation values, which in this case vary in time because it's a superposition state. We could calculate the uncertainties in position and momentum for this superposition state, and we could verify that we are obeying Heisenberg's uncertainty principle. But the math is a little messy, and we wouldn't really learn anything, wouldn't learn much, so we're going to skip those. Let's look at a simulation of particle in a box in one dimension and some other things. There's a nice simulation capability of particle in a box in one dimension from Paul Falstadt's website, falstadt.com, mathphysics.html, and the particular simulation we're going to run is QM1D, quantum mechanics in one dimension. This is really helpful for seeing wave functions and time dependence of superposition states. I am going to insert here the video of simulation that I did from another class. There's no transcript for my commentary here. So just watch the video, and if you're adventurous, go to that website and play with it yourself. Here we are at falstadt.com. We're going to click on Math and Physics Applets. He has applets for a number of math and physics cases: oscillations and waves, acoustics, signal processing, electricity and magnetism, electrodynamics, quantum mechanics, hydrogen atom applet. That's pretty interesting. We're not going to cover that. Molecular orbitals, lots of interesting quantum mechanical stuff. We're going to look at one-dimensional quantum mechanics applet. Now, We can choose different problems: infinite well, finite well, harmonic oscillator, other things. We're going to look at infinite well for most of our time, and then at the end we will look at finite well. We have different portions to the screen. This upper portion is showing us different energy eigenvalues. It's hard to see down here because they're closely spaced, but you see that they get spaced out more as we go to higher values. I don't think I can expand this section to show us. Now, this second section here, I currently have it showing us the probability density. So that's this curve. And you see that the color is changing. That's the phase. Phase is getting mapped to colors. I'll change this a little later and show you different things. The red line here is showing the expected value of position. We're in the ground state right now. So the probability density is symmetric with respect to the center of the box, and there's no node, and the expected value of x is the center of the box. I'm going to make the box a little smaller so that you can see that it is 0 outside the box. Now this third pane here, the third pane here is momentum, but I can't expand this horizontally, so it's hard to see the momentum. This fourth pane here, this is called phasors. It's the amount of different eigenfunctions that are included in the wave function, the amount and phase. I'll explain this a little later. Now, we can view the wave function as probability or as the wave function, but the wave function is complex, so it has a real part, an imaginary part, it has a magnitude. If we want to look at the wave function, not the probability, well, let's do real and imaginary parts. The real and imaginary, we're in the ground state, the real and imaginary parts are changing in time. You know, we know that because it's the time dependence is e to the minus I e sub 1 t over h bar, so the real and imaginary parts are changing. Let's see if I can show us, if I can get it. Okay. Now I've changed from the ground state to the first excited state. There is a node at the center of the box now. So we're seeing the first excited state wave function, real and imaginary parts. We're seeing the real and imaginary parts of the momentum here. We could look at higher energy eigenstates. I'm going to change the view so that we look at probability plus phase. Now, when we look at probability plus phase of an energy eigenfunction, here we're in the first excited state, The shape is not changing in time, but the colors representing the phases are changing in time for both position and momentum. Now what we're going to do is create a superposition state consisting of the ground state plus the first excited state. And when we do that, we see that the probability density, which is this pane here, the probability density is changing in time. It's sloshing from the left side of the box to the right side of the box to the left side of the box periodically. The expected value of position, the red line here, is changing sinusoidally in time. The momentum is changing also, but it's too clumped together on this display for us to see very well. We can speed this up some. Here's low mass. And for large mass, the energy levels became closer together. And the energy levels became smaller, the energy eigenvalues, and so the period became larger, so slower. Ah. I encourage you to play with this yourself. Now we're going to do something that the simulation allows us to do. We're going to measure the energy. We're in a superposition state consisting of the ground state plus the first excited state. When I click this, we will measure energy. When we do that, we collapsed to, in this case, the first excited state. Now, if we remeasure energy, we can remeasure energy all we want, and it's always going to, we're in an energy eigenfunction now, so measuring energy is not going to change anything. Let's see if I can go back. Back to a superposition state. and tell it to measure energy again. This time, just randomly, we ended up in the ground state. Let's see if I can get us back there. Okay, we're back in the superposition state. Now I'm going to ask it to measure position. What do you think will happen? Boom! Look at all these phasors. When we measured position, we got a value of position. We don't know what it is, but we then got put into a state which is not an energy eigenstate at all. It's a combination of all of the energy eigenstates. It's a superposition state, but boy, it's not a simple superposition state. Look at how complicated the system is now. Let's go back to ground state. Okay, I encourage you to play with this. Get a feel for superposition states and for energy eigenfunctions, a nice graphical feel that you can't really, you can get to a limited extent with equations and graphing, but the simulation is really helpful. Now I'm going to do one other thing. I'm going to go to finite well. We didn't do the math for finite well, but I said earlier that for finite well, we can have probability density outside the well. So in this energy eigen, it's hard for me to show it because if I move the cursor, so if you look right below the cursor, you'll see that outside of the well, to the right of the well, there is non-zero probability density. It's an decaying exponential, but it's not zero. In the infinite well, it was zero. But for the finite well, there is non-zero probability density outside the well. Now let's reduce the well depth. Can't really see it very much anymore, but I broke the simulation. It turns out in one dimensions, no matter how small the well is, the depth of the well, there always is still a bound state. That need not be true in 2 dimensions and 3 dimensions, but in 1 dimension it is. Let's reduce the well width. Here we can definitely see that there is probability density outside the well for finite well. Okay. If you want, you could play with harmonic oscillator. Or 2 wells. or other cases. This is the end of the third of 4 videos for this course.